All right, section 7.2. Anti-differentiation with substitution rears its ugly head again. So back in the fall, we learned several different ways to antiderive, or different types of functions that we could antiderive. And I mentioned at that point that the book will come back to antidifferentiation later. We will give you some more kind of rigorous mathematical context for why it's relevant. That would be the fundamental theorem of calculus. So I promised that we would come back to it, and here we are coming back to u-substitution. So let's remind you of a few things before we get into this. This first part of 7.2 will just be talking about antidifferentiation using u-substitution in indefinite intervals. So it's worth talking about the difference between definite intervals and indefinite intervals before we go on here. So first of all, something like this, where there's no upper and lower bound, this is the notation I told you guys we would use when we were anti-deriving. So I essentially said, hey, this notation means take the antiderivative of f of x, which is the integrand. Okay. Now we've learned where this dx comes from and where this comes from, the integral symbol, where that comes from. We learned that in the last chapter. This is called an indefinite interval. Okay, and when you take the antiderivative of this, remember that you get a family of functions. So let's put that explicitly here. So a family of functions. All right. Now, that is in contrast to, and remember, so a family of functions, because when you take the antiderivative, you always had to put plus c, because we weren't really sure what it was possible there was a constant, right, that we took the derivative of and got 0, getting to lowercase f of x here. All right, so the next thing, so that is in contrast to a definite integral, which would be something like this, the integral from 1 to 4, let's say, or from a to b, or whatever it is, of f of x dx. This is called a definite integral. Okay, and a definite integral is an area, right? So this outputs a value. Okay, so these look very similar, but they mean very different things, right? This is an area under a curve. This is a family of functions. Okay, so we don't need to spend a lot of time on most of the derivative rules because they showed up in the last chapter when we were doing definite integrals. But u-substitution was completely left out of the previous chapter, and it shows up here. So let's just get right into some examples and hopefully kind of refresh your brain on u-substitution. So if we were given something like this, the integral of sine of x times e to the cosine of x, we would look at this and go, oh, well, I can't really antiderive right away, right? Because this is not like a, x squared or x to the 3/2 or something like that, or just sine of x, where I can just straight up kind of reason my way backwards to what the derivative would be. You may be able to figure out what the derivative is based on what you see here, but there's a more systematic way to go at it, and it is this idea of u-substitution. So the whole idea there was, if you can figure out a u, it will simplify the integrand so that you can more easily antiderive it. So in this one, the u is going to be cosine of x, right? Now, when we talk about how do you choose the u, in lots of cases, you only have a few options, right? So you could pick sine, you could pick cosine. Those are really your only options, right? And so if you pick u as cosine, what you're thinking is, well, if I can get this integral down to something like e to the u, well, that would be easy to antiderive, because the antiderivative of e to the u is just e to the u. So if I pick u as cosine, then du is equal to negative sine of x, well, du dx, excuse me, is equal to negative sine of x. And remember, we said we can kick the dx over to the right-hand side. Probably won't even show that step on the future problems. And then let's move the negative over to the left. So we get this, du is equal to negative sine of x dx. All right? And so that works. Sorry, let's kick the negative to the left here. Okay, so this works because sine x dx matches sine x here and dx here. All right? So in place of sine x dx, I'm going to put negative du. All right, so I have a negative. I'll just put the negative out in front of the entire integral and du here. Okay, so now I can go and antiderive e to the u. Don't forget about the negative. So the antiderivative of e to the u is e to the u plus c. And then always remember that your substitution initially, u was cosine, so now we can put cosine back in there. Remember that you can always check your answer by deriving, right? So if you had nightmares about u-substitution in the fall when we learned it, sometimes when we come back to it in the winter, it actually makes a lot more sense. So hopefully that's the case for you. We'll do a couple more examples here just because there are a number of different ways that u-substitution can be applied. And then hopefully by the end of the video, you'll feel a little bit more comfortable with u-substitution. Okay, so let's do another one here. Let's look at the integral of x squared times the square root of 5 plus 2x to the third dx. Okay, so first thing you've got to do is pick your u. Usually, u is going to be the inside, like it will look like it's inside of something else, okay? So that's kind of where you can kind of start as far as trying the u's. And remember, if you try it and it doesn't work, then just go back and try it again. Or try something different, try a different u. So let's set u as this piece right here, 5 plus 2x cubed. All right, so then when I take the derivative, I will get du is equal to 6x squared dx. So this is close, right? I have x squared dx, this is 6x squared dx. So what I'm going to do is move the 6 over to the left here. So I get this, 1/6 du is equal to x squared dx. And now in place of x squared dx, I'm going to put du, well, 1/6 du. And so I will end up with 1/6 on the outside of the integral. In place of this, I'm going to put u. So I'll have u, I'll just put that to the 1/2 because it's a square root. And then x squared dx is 1/6 du. Now I can antiderive. So I get 1/6, add 1 to the power and divide by it. So that is going to be u to the 3/2. Divided by 3/2 is the same as multiplying by 2/3. So that'll be 2/3 in front. My screen has frozen. One moment. And we're back. So anyway, 2/3 u to the 3/2 plus c. And then we can just finish this out. So this will be 2 over 18, so 1/9. So 1/9, and then u was actually 5 plus 2x cubed, so 5 plus 2x cubed raised to the 3/2 plus c. And there you go. That's the original, the function whose derivative is that mess right there. Last one. The integral of cotangent of 7x dx. All right, so this one, we're going to actually have to use a trig identity to help us out because there's no obvious u du situation. If you pick u as 7x, you get du is 7, and that doesn't really help you. So what we're going to do is we're going to change this cotangent to cosine over sine and see if that helps. So we'll change this to cosine of 7x over sine of 7x. All right. Now we try to think of what would be our best choice for u. We could pick cosine of 7x. When you derive cosine, you'll get negative sine 7x dx, which doesn't really map onto what we would need for the du, because sine of 7x is in the denominator here. So we would want like 1 over sine of 7x. So what we'll try then is sine as our u, sine of 7x. So let's write that down. And again, if you make a mistake, it's fine. Just go back and try a different u. So in this case then, du will equal cosine of 7x times the derivative of 7x, which is 7, dx. I'm going to move the 7 over to the left, so I get 1/7 du is equal to cosine of 7x dx. And you can see then right here, cosine 7x dx, that's my du. And then sine of 7x right here would be u. So I get this. 1 over u du. And don't forget the 1/7 comes out in front of everything. And then the antiderivative of 1 over u is 1/7 natural log of u, absolute value, plus c. It's the absolute value because this is defined for all real numbers except for 0. Natural log without the absolute value is only defined from when x is greater than 0. So that's our antiderivative. Last step, plug in u. So 1/7 natural log of the absolute value of sine 7x. Right, plus c. Okay, and that's it for the first part of 7.2, the refreshing your understanding and knowledge of u-substitution.